Okay, let's try that again.
Hi, welcome to the VAPALS ELCAP OSEHRA Working Group meeting for Wednesday, February 27th, 2019. Um, as usual, we're recording this call so that all of you can have the joy of watching it again because since Rick is presenting today, you'll probably need to. Luckily, he's entertaining at the same time. So, anything that anybody wants to announce before Rick tells us more?
A quick status update on the user-facing features on VAPALS ELCAP would be that Dom and George are working on the latest modifications, which I think we mentioned last week and the week before, that came from the LCAP group about the refinements that they wanted. So all of that's in progress, and as soon as it wraps up, we'll present it on the next one of these calls where it's ready. But until then, we'll have these technical calls.
Okay, well, you may as well take it away. I should probably give you the presenter's rights unless you've already taken them.
Okay, then let's do that. Hi, everybody. This is Rick Marshall. I'm going to do part 3 of the series that we're doing on how to configure VAPALS LCAP systems. And as part of that, we are having to invent some new standards and conventions for reasons that will become most apparent on this third call. The basic motivation here is as follows. With the VA heavily distracted by the Cerner initiative, which it sure will solve all of its problems, there is not a lot of focus on manpower available to manage the existing systems, let alone these new servers that we want to stand up at the VA. So that means that these systems, these VAPALS LCAP systems, have to be managed differently than the existing Vista systems are managed. The existing Vista systems require a lot of manpower to manage because they have a direct impact on patient care. People have to be watching them like a hawk and make sure that they're healthy and intervene immediately if anything goes awry to make sure that there's as little disruption as possible. Plus, these things are not commodity products. They need to be constantly updated with patches to support breakthroughs in computer science, to support breakthroughs in medicine, and to support changes in law and policy, because you're not allowed to be too far out of sync with any of those 3 domains. So there's a constant stream of upgrades going into these systems, and that was always designed to be the methodology that the VA uses to upgrade its systems has always been designed to piggyback upon the manpower that they had to put on the systems anyway. Since somebody already had to be watching these things like a hawk, they went ahead and added a bunch of manual processes for upgrading the systems. And although the automation is, the amount of automation that's available has improved over the decades, it's really has not been designed as to be a system for upgrading that's as automated as possible. They never pushed it as far as they could. It still requires an enormous amount of human time and energy. And I'm not talking about temp workers. I'm talking about serious, experienced, in-depth expertise to upgrade these systems, which has to be done all the time. So we're basing our system on the same technology. The VAPALS LCAP server is a Vista system to which we have added a Vista application, a new portability layer called Mash, plus various upgrades to the Vista environment. And because it's a Vista environment, that means as the Vista servers that they're using to take care of their hospitals are being upgraded, our servers also need to be upgraded. But they don't have the manpower to spare to upgrade our server, so we have to use a different approach. For us to use a different approach, we finally have to crack the egg that the VA has kind of not focused on all these decades. That is, we've got to make it much more automated. We have to make it so that it requires as little human intervention as possible and as little human time as possible to upgrade one of these servers. And that means we're going to be writing a lot of automation tools. And the only way that that's possible is if we standardize a bunch of things that the VA never bothered to standardize. Things they didn't standardize because they already had human experts who were full-time looking at their servers and knew all of the fiddly little details that were different on every different server. So it was fine the way it was. But for what we're doing, if we're going to write automated scripts and tools, it can't require a whole bunch of idiosyncratic knowledge that's specialized to some expert who's been working there for 40 years or 30 years or however long it's been. We've got to standardize the layout of these VAPALS ELCAP servers so that things are in predictable places, and the format of those things is also predictable so that we can write the tools to do the automation, so that somebody like Ardit, who hasn't been supporting a Vista production system for 30 years, could nevertheless connect into one of these servers with our little package, run a handful of scripts, and it should automate the environment for him with his, not requiring him to magically, in addition to all of the other domains of expertise that he carries around in his brilliant head, we don't have to somehow also give him brain surgery and transplant a Vista System Manager's brain lobe into his head as well. We'll do that through the automation tools, and that way what he already knows how to do will be sufficient to upgrade these systems. So this is the payoff. This is why we're spending all this time talking about this. This is, and it's why we've put so much energy into this, is because this is an area that the VA has been able to ignore, but that we can't because of the nature of this project. So we're taking this opportunity to solve these problems in very standardized ways that draw off of a bunch of other initiatives. But you'll see that as we go. The goal, we're big fans of standards. we're crazy for standards. So we're drawing off of existing things. We're not inventing this stuff from scratch. So in the previous two sessions, we walked you through the idea that there are different kinds of repositories that serve different functions. Some repos are used to distribute software. Some repos are used to analyze the contents of an existing system, which we need to do for Vista standardization and other initiatives. And we talked about that we would use standardized directory structures for where we would put those repos and where we would clone them and sync them and do our pushes and pulls and so forth. But we haven't gone into a lot of detail. We just wanted to give you the top level picture of kind of what we're after. And the reason that we did that is that before we can get to the punchline, which is exactly how are we saying a repo should be laid out and exactly how are we saying directories should be laid out, there's just one obstacle in the way. And that is, what is a Vista system? What is a Vista environment? What are these things that we are attempting to upgrade and or analyze? And this does not have a simple answer, as you will see, but it is a comprehensible answer. And by the end of today's call, you will understand it. You will get it. So on the first couple of calls, we introduced the patch stream architecture. We introduced some of the namespacing schemas. We talked about the fact that there are different dialects of Vista and that your patch stream should be the one for the dialect that you're running on your server. You don't want to be installing IHS patches onto a VA production server unless you've done a lot of careful analysis to make sure that there's no collision, because there's a high likelihood of collisions and so forth. So we had to figure out what are those dialects and give them all codes, and what are the different developer/development shops that are responsible for dialects and give them codes. And then what were the systems by which adopters were given their own codes and namespaces? And based on that, how can we namespace and identify sites that have multiple Vista systems? And how can we identify systems themselves? And so this is what we went through. This is as far as we got as of last call. And I'm not going to rehash it. I just walked us through it as to relay the trail of breadcrumbs. For anybody who's coming to this third call in the series without having gone to the other two, wow, you want to press stop and go watch the other two in order first, because the more you understand this stuff, the easier time you're going to have with what's going to come next. So what's going to come next? Well, here it is. MUMPS is not a programming language. First classic error. MUMPS is a backronym, which is where someone invents some words that can fit an acronym that they thought would be a clever thing. So it stands for Massachusetts General Hospital, which is where MUMPS was invented, Utility Multi-Programming System. And it says it right there in the name. It's a programming system. And the difference between a programming language and a programming system is enormous. A programming system includes a programming language, but it also includes a database. And it includes system management facilities. It includes transaction management. It includes device management. There's a whole bunch of kind of environmental ideas about what a computer is that are folded in. And the MUMPS language, very different from assembly language or C or a lot of other languages, as much as possible tries to insulate you from the details of what your actual hardware looks like. And the reason it does that is the more locked into the current details of the hardware you are, the more obsolete your software is going to be when you change hardware. right? There is an enormous problem in the computer science world, which is that almost everybody reinvents the wheel. They have to invent it for the old 386 computers, then they have to invent it for the 486 computers, and then for the Pentiums. They have to invent it differently for the Linux boxes, for the VAXs, for the PDPs. All these different pieces of hardware, handle devices differently. They handle databases different. Everything is different. And if your software is locked into that, then when that piece of hardware becomes obsolete, so does your software. And that we cannot afford to do that in medical software, because medicine and computer science and medical policy and law change so fast that it's all we can do to keep up with them. We can't also be every few years throwing out everything we wrote and starting over again. So like when user interfaces change, if we go from dialogue terminal oriented screens to a screen at a time forms, to doing GUI windows, to doing web browsers, again, we can't be chucking all our software and starting over. We don't have that kind of time. Medicine is changing too aggressively. We've got to, it takes everything we can do to keep up with that. So MUMPS solves this problem by creating a virtual machine. The MUMPS programming system defines an imaginary abstract computer, and that's the computer that we program against. And it's the job of the implementers who write a version of MUMPS for us to connect the dots between that abstract machine and whatever machine they actually physically run it on. So, for example, Digital Standard MUMPS, which was created by Digital Equipment Corporation in the 1970s and 80s and 90s, it had to satisfy the MUMPS virtual machine definition as described in the MUMPS standard. And we all programmed to that, assuming that the disk works a certain way and memory works a certain way and so forth. And then it was the job of Digital Equipment Corporation to write a version of DSM that connected the dots properly when it was running on a PDP, which was very different from a VAX, which was very different from an alpha. They were the ones that had to solve that problem. That was none of our business. And so as long as we wrote to the virtual machine when Digital came out with their new VAXs, which were so much more powerful and interesting than the PDPs, we could take almost all of our software, over 99 point several nines% of the Vista software could be picked up and dropped onto this new hardware with no changes at all. It was just a few dozen routines that we had written that provided a little bit of extra insulation to open up some of the features from underneath. Those were the only ones that the kernel and FileMan teams had to change. All the rest of the software, it just ported right across. That is what gave Vista the ability to surf the hardware revolution. As hardware massively changed every few years from generation to generation, as operating systems massively changed, our software didn't have to. We could focus, instead of wasting all our time rewriting everything to run on the new platforms, we could add CPRS, so that we're now doing doctor's applications. We could add Vista imaging so that we could focus on the medicine and constantly be upgrading the feature set that's available. So the point is, if you're going to run MUMPS, that is to say, if you're going to run VAPALS ELCAP, you're going to run it on a Vista system. If you're going to run a Vista system, you're running it on the MUMPS virtual machine. And so if we're trying to answer the question, how do we lay out the directories? How do we lay out our repositories? And where do we put this thing? All of which we might call the problem of configuration. To answer that, we really need to understand what the MUMPS virtual machine looks like to Vista. Until we know that, we don't know anything else, because you can't get Vista running unless it's satisfied that the virtual machine looks the way that it thinks that it looks. A certain amount of configuring Vista is filling in fields and parameters to tell it, this is where you look for this, and this is how you access that thing, and this is the version of MUMPS you're running on. You have to give it some basic information so that it knows what's underneath it, so that it can hide that information from most of the rest of Vista, so that it can put in place the little platform that supports the rest of Vista. That little interface layer at the bottom of Vista, configuring that correctly, is largely about doing some of that connect the dots work. So that's all based on Vista assuming that the virtual machine in MUMPS works a certain way and has certain features. So I'm going to walk you through what those features are, because you have to know what they are. You have to speak that language. You have to be able to it's like if you're trying to play chess and you don't know what the pieces are, you're not going to get very far. So I'm going to teach you the pieces of the MUMPS virtual machine and how it works. And this is going to take a few slides, but each slide is just going to share a few ideas. It won't be too hard for you. And we're going to walk through a little history here, a little evolution. I'm going to take you through the way that it started, because some of those old ideas are still present in the kernel. You've got fields and files that are named after the way things used to be. And so we're going to walk you through the process of change that's happened so far, and then the final few steps of change that are required for us to set up our VAPALS and VAPALS ELCAP servers. So here we go. When it all began, the basic idea, and all of this is still present in some way, is that mumps jobs run inside of a mumps virtual machine. Now, that's one of the things that's changed, and we'll talk about that change later. But the idea was that the machine itself, the computer that you were running on, had no operating system. Mumps was the operating system. And so when you woke up your machine, one of the first things you had to do was wake up Mumps. And when users wanted to do things in Mumps, they had to knock on the door, and Mumps would answer and challenge them to say to prove that they deserve to be on the system. And if they could meet the challenge, then Mumps would start a job or a process, and that job would run inside of the Mumps virtual machine. And so that Mumps job didn't really see a lot of information about the machine that it was on. It could be a PDP 1184, PDP 1144. It could be a Plessy. It could be there's a number of different hardware that we had Mumps virtual machines running on, and mostly we didn't know. Here's what we knew. We knew that we were inside of what was called a user class identifier, or a UCI, and there was only one or maybe only a few of these on the whole system because you didn't need very many of them. The purpose of a UCI was to have a set of directories, and the directories contained within them are the resources that Mumps jobs need. So Mumps jobs need software they can run. And Mumps software is called, instead of programs, we call them routines. They tend to be shorter so that we can swap them in and out of memory more easily. And the list of routines, the complete directory, like a Yellow Pages, if you will, where every routine has to have a unique name, the complete routine directory is one of the things that a UCI contained. Likewise, we did in the classic Mumps world, we didn't have files. Right? When you do a word processing and you create a file and you share that file with your friends, we didn't have anything like that. And there were a lot of good reasons for that, which I won't go into on this call. What we did instead is we took the idea of variables, which people are used to from programming, and we just put a little up arrow, the little shift 6 in front of it, and we said if that character is in front of the variable, then instead of being a temporary throwaway variable that gets discarded when your job is done, it's a permanent shared variable that's on the hard drive, and all the different Mumps jobs can see all the variables that have been defined. So they're called globals. Global variables are the variables that are shared and persistent. That's where we do our database work in Mumps, and we therefore needed a directory that listed all of the globals and had all their contents. So that's what we did instead of files. The global directory is where we kept our data. The routine directory is where we kept our code. The lock table is how we coordinated access to the globals. Two different jobs want the same global. If they're just reading, that's okay. But if they both want to change it, to avoid database corruption, Mumps includes the ability for them to coordinate access so that only one gets in at a time. And they do that through locking, and they lock a name of the global, and then the other guy tries to lock and he fails, and that's how he knows he has to wait. And the one who's got it can do his update, and then he can release the lock when he's done, and then the other guy gets the lock, and now he can do his update. So there is this process by which they it was like a traffic, it's like having a bunch of traffic cops. And so the list of lock names is also something that's contained inside the UCI. Those things together make up a UCI. And then the UCI was contained inside of a larger thing called a volume set, which was a group of UCIs. And so you might, for example, have a UCI that all your admissions people sign into. And you might have a separate UCI that all your pharmacy people sign into, and a third one that all your lab people sign into. So all the lab data and the lab code is in the lab UCI. All the pharmacy data and the pharmacy code is in the pharmacy UCI. And all the admissions data and the admissions code is in the admissions UCI. So that would be the general pattern that we followed originally. And you can see that pattern here on my second diagram, where on this same computer, this is sort of a prototype notional configuration for how Vista systems could be set up. You could have some jobs that were connected to the admissions UCI, and that would be for admissions clerks. And some jobs would be connected to the pharmacy UCI, and those would be pharmacists. And some jobs would be connected to the lab UCI, and those would be lab techs. And then there would be a shared UCI for managing the system. And that would have startup and shutdown and, configure the global database and the sorts of things that sysadmins need. And then it would also have things that are shared. If there was information that all three of those UCIs needed, we would give it a special name with a %, and we'd stick it in the manager UCI, and then they could all see it. So we had a way to share between UCIs, and otherwise data would be separated. And this was our basic security and our basic model for how information was organized. And here you can see the purpose of the volume set more clearly. The volume set says, all of these UCIs together are one collection. They can be managed together. We could add more UCIs to the volume set. We could add other volume sets that could have their own UCIs. It allows you to do partitioning and segmentation of, which was really essential for these systems. This whole process that we're talking about here is called configuration. And in the early days, the trailblazers who went out and figured out how to get these things to work would write a manual called a Vista Cookbook. And the cookbook would be a description of here's how you use your computer and use your MUMPS implementation, how you configure them to set it up so that you can run Vista in this environment with reasonable performance, right? And these kind of sysadmin experts at the national level would be constantly tinkering with the cookbook, trying to get these systems to go faster and be able to store more data and be able to get more users on them and things like that to really tune them up and get some performance out of them. I mentioned the MUMPS implementer. I'm going to say it again. The basic premise in the MUMPS community is that we have a MUMPS standard. The standard defines the language. When we write software, we write to that standard, assuming that the virtual machine works that way. And then different companies or individuals can write implementations of MUMPS that we could then install. And as long as they comply with the standard, we can then pick up our software and move it onto the new MUMPS implementation. So that allowed us to create a marketplace of competing implementers, which helped to drive down prices and drove up innovation. That was built into the whole MUMPS idea. In addition, jobs need to be distinguished from each other so that the sysadmin can look at them and figure out which one is eating up his system and which one is just fine and he should leave it alone. So they all have job IDs defined in MUMPS. And MUMPS doesn't say exactly what it is, but typically it was a number, 1, 2, 3, 4, 5. And the idea would be that when you're on a given machine, that machine is where you're getting your numbers from, 1, 2, 3, 4, 5, 6. So if I had two different, well, as you can see here, I've got 3 different UCIs, but the job number, the pool of job numbers, the unique pool is shared between them, right? So the pharmacy UCI there has jobs 3 and 4. It can't have a job 1 or 2 because they already exist. They're running on admissions. And so that's how we can identify the jobs and distinguish them from each other. That's how we identify the UCIs. They have their little 3-letter names. That's how we identify the volume sets. It has its little 3-letter name, and so forth. The other thing that was here, which became very important next up, was sometimes you have to write software that it might be admissions software, except it might need to do something with pharmacy. It might need to tell pharmacy something about, something important that just changed. So we needed the ability to write software that you could be job 1 and it's admissions job, but it needs the ability to reach over and either read or write from the pharmacy UCI's global to say, oh, this guy changed his name. You better update your pharmacy file because this guy's name is now this. And so we had this idea of an extended reference. Instead of just doing a routine up arrow run me, or writing a global up arrow data, if we needed to access a different UCI, we would insert this little syntax here, which is a left square bracket, a quotation mark, and then the name of the UCI, a quotation mark, and a right square bracket. This is called an extended global reference or an extended routine reference, depending on which one you're doing. And it gave us the ability to start to weave together the data in these different environments. When we first got started, pharmacy really was pretty much separate from lab, which pretty much was separate from admissions. But anybody who's familiar with Vista today or thinks about medical software generally can see the obvious limitations of that approach. Pretty quickly, you run into scenarios where they do need to exchange information between systems. And so we have to move away from this idea of vertical silos and move into an idea of integrated databases and integrated software. And so one of the first steps was to get the ability to do little extended references, to reach across. And that required us to have names for UCIs that were unique. And eventually, sometimes it required us to have names for volume sets that were unique, right? Then we might have reasons to put a different group of UCIs somewhere else. And if for some reason we needed to reach over there, well, that volume set couldn't also be named ROU just like this one, or else the MUMPS wouldn't know what we were talking about. It would think we meant this one. So unique volume set names, unique UCI names, these are all important to creating an integrated system. So this was the prototype. This is how we got started. But the problem was, back in those days, the PDP-11s were just not that powerful. Having the admissions clerks and the pharmacists and the lab techs on the same computer worked when you had a teeny tiny little hospital. But as you got more and more users on there, it didn't take long before you had too many pharmacists and too many lab techs and too many admissions clerks, and you really had to separate them. So we shifted to a new model in which we broke them up into separate machines, right? And so under this model, you could have the volume set ADM for admissions and PHA for pharmacy and lab for lab. And then each one might have its own manager UCI MGR, and then it might have a production UCI like LIV for live or PRD or PRO for prod or whatever. But at this point, the different kinds of users would connect to a different machine, right? So there was a different way to do segmentation. So this idea of what is the relationship between a UCI and a volume set and the MUMPS virtual machine and the hardware underneath it, it varied over time. It changed. It had to be flexible to allow us to evolve. And as a result, the Vista software has built into it a great deal of flexibility as far as thinking what is the relationship between a UCI, a volume set, MUMPS in general, Vista, the hardware. It's got various pointers and configuration files you can set up to say, well, this time we've configured it this way. Next time we might configure it a different way. Notice here that because we're talking about different machines, the job numbers start over, right? On the previous model, we only had a single computer and it was assigning the job numbers. So the pharmacy job numbers couldn't overlap with the admissions job numbers. The numbers were coming out of the same pool, right? Typically, it's the machine that's assigning the number, which means if you've got multiple machines, you can be reusing job numbers, right? You could have job one on the admissions machine, but job one on the lab machine is a different job. It's a lab tech running against this other UCI and volume set over here. So that meant that if you were trying to do troubleshooting, or if you were talking over the phone and you asked somebody what their job number was, under the old configuration, the prototype configuration, if they said they were job 3, you knew exactly what job that was. But now if they said they're job 3, you also have to ask which machine they're on, because it's job 3 on which machine. So there's an identification problem that comes up at this point. So this was typical of early configurations, but this caused problems because now the data is even more siloed than it was before. So at the same time that was being developed, the national developers needed systems for themselves. And likewise, the local sites needed additional systems where they could experiment with code that wasn't ready to run in live yet. You can't just have a system in which the only environments you have are live environments, or else the process of change is extraordinarily disruptive. You need the ability to not only, if necessary, silo different kinds of software from each other, but software at different stages of maturation. You have to be able to silo from each other. And so another way to use UCIs was to separate your production environment from your test environment, from your development environment, so that your really disrupted area over here is not directly impacting the live users. And you can try it out in test and have the live users sign into it and test it until they sign off and tell you, okay, we think it's ready. And then when it is, then you install it into production. So this kind of process of staging and working your way over to where it's ready to run in production is one of the really important ideas that developed in the early world of the MUMPS Vista world. And this pattern is typically followed to this day in some form. It's essential. Whereas we no longer separate admissions and pharmacy and lab from each other because medical software has come further than that, we do still have to separate the different stages in the development of the software from each other. Now, what you see here has its problems. And one of the problems is, what if the software that you're testing includes software that updates the manager UCI? That's the shared software between all 3 UCIs. So your production UCI, most of the software is here in this UCI, but the shared stuff is up here in manager. So over here in development, I try out some new idea and it really blows things up. And part of what blows up is over here in manager. Now, I didn't just blow up my development UCI, I also blew up my test and production UCIs. So that's not okay. So this model here became problematic, and we realized that just like we had to move from this production approach to handling different applications to a siloed approach, we had to do the same thing here and really separate the test environment and the development environment onto different servers. For an example, if you develop a really great report that just goes through the database like crazy and compiles all kinds of data, and it's just massively intense on the disk, well, even if you didn't break anything production, now nobody in production can get anything done because the system's so slow because of what you're doing over here on test. Larry's raising his hand saying, me, I did that. Yeah, those of us in the old days, we all did that. So we really don't want to follow this model anymore. This is just a prototype life cycle configuration. What we really want to do is create a safer life cycle configuration in which we separate them into different little silos. And when we're doing that, we typically don't try to name the volume sets differently. Oh, and I said admissions pharmacy. That should say this here. I didn't rename. It says admissions pharmacy and lab. It ought to say okay. This was a little hurried. This should be the test UCI. This should be the development UCI. And this should say development volume set, and this should say test volume set, and that should say production volume set. Yeah, this is what comes of racing through this thing from 6 in the morning, getting all these things put together. But the basic idea is still here. We basically did the same thing with lifecycle configuration that we did with separate applications. We siloed them from each other in order to isolate the impact, and that meant, for example, that I've talked about what it meant here in terms of development and test and production. It kept them out of each other's hair. What it meant back here in the old days is when we were talking about separate applications and separate silos, it meant that if something really went haywire with lab, only the lab users were affected, right? The pharmacy users had their own machine and it was fine. And then the admissions people had their own machine and it was fine. So segmentation by machine is a really important principle for system management. You really need to be able to put up firewalls that limit the damage. And these were different strategies that people took for them. All right. So the third dimension of this that we have to talk about is failover, which I guess we'll come to in a moment. But one of the stages to getting to failover was this idea: what if one machine isn't enough? What if you have a lot of pharmacy users and they're really busy and they outgrow one machine? Maybe they need 2 machines now, right? So how do you do that? Mumps came up with these ideas called replication and translation, and we're talking back in the 70s and 80s here. So this is some early stuff. And the idea was, sure, you stand up 2 different production machines, but you could have the same contents in both, as long as if somebody updated one of them, it copied the data across to the other one. That would be replication. Or when you thought you were updating the data here, it translated into a network access over to here. So really, you're only updating the data in one place, but it's visible in 2 places. So these are 2 different strategies for making it possible to have users on 2 different computers who think they're working on the same database, right? It's either a copy that's being kept up in live time, or there's network accesses hidden. As they reach for the global they think is right here, it's actually reaching across to the global that's on the other computer. And the MUMPS implementers worked all this out years ago, decades ago at this point, so that it would be actually reasonably fast. And this created a new idea. These kinds of replication translation configurations made it possible that now we could add more and more and more machines to what was effectively the same MUMPS virtual machine. Really, it was effectively the same MUMPS volume set, or UCI, the same set of globals, same set of code. Even though practically they might be copies of each other, or they might just be sort of standing in for each other and being translated across. It created the effect of being able to spread out across multiple machines and create to get more horsepower into it, to get more which let me tell you, in the late 80s was a dying need. I mean, like 89, 90, around that time, when the VA desperately needed to upgrade its computers but hadn't yet got permission from Congress to do so, it was often very painful, very, very poor performance for extended periods of time. And also the systems, even when they had good performance, were very fragile. One heavy job out of place and all of a sudden nobody could get anything done. So we were real excited by this breakthrough of being able to do replication and translation to throw more hardware at the problem, to get more and more computers working together, looking at the same environment. And as you can imagine, there's a lot of database integrity issues that come up with this. How do you make sure that the updates are applied to the globals in the right order? If guys on one machine, another guy's on another machine, how do we know that they're updating the data, that they're seeing the data the way it really is, and not a little out of sync with each other, which could lead to corruption? All that stuff got worked out back then. It was exciting time. So based on that, once we knew that that was there, we did what's called a failover configuration. In a failover configuration, we use replication. So we're only using the primary machine, and all the users are signed into it. And as they update the data, their sets and kills, their changes to the database are copied over to a copy of the environment on a secondary machine. And now, if the first machine crashes, you can have all your users sign back into the secondary machine, and all the data's there. They haven't lost anything. You might only get minutes or seconds of downtime, whereas before it could be, might have to go to backups and translation. And for medical systems, you can't afford to have them down for very long. That you could in the early days when they were experimental and people are like, well, I'm just going to keep using my chart here, but I suppose sometimes I'll use this newfangled computer thing. But the more people liked computers, the more they relied on them, the more important it became to keep the systems up all the time. And so we had to switch to a model in which there's always a secondary that the data is being replicated to. And at any moment, if the primary drops, you can switch over to the secondary, because the data's all been replicated the whole time that it was updating on the primary. You've got copies of it on the secondary, and boom, you're off and running. And while people are on the secondary, you can then fix the primary, or you could bring a spare, your test machine. You might kick all the testers off and save off the data and bring it into Harness as a new secondary for what was your secondary but has become your primary. You start swapping it around to put inserting safety nets under the systems, as it were. This was the sort of things that sysadmins thought in terms of. So again, when we talk about UCIs, we talk about volume sets, we talk about systems, this really covers the original scope of the idea. These are what the virtual machine looked like from the perspective of the early days when we were first getting started. And a lot of the configuration fields and files in Vista still talk about the world this way. There is a UCI file. There's a volume set file. We have files where we talk about parameters that affect a volume set if you're on this machine in that volume set versus if you're on a different machine. Because after all, if you've got multiple machines, what if one of them's not as powerful as the other? Maybe you don't want as many users on the less powerful one. So you'd like to set different configuration limits. You might say, well, for the more powerful machine, there could be more users, but for the less powerful machine, there could be fewer users. So we've got files for these sorts of things to set these limits at different levels and allow us that kind of flexibility. Well, all of this sort of got started back in the era when there weren't operating systems per se. I went back and looked at my old copies of the MUMP standard, and in 1984, they did introduce the word operating system, but they didn't mean it the way we meant it. They just meant, something somehow is running the computer. MUMPs really didn't think about the idea that there could be something between MUMPs jobs and the hardware other than the MUMPs virtual machine. That was it. So MUMPs virtual machine, the physical machine, and then nothing else. That's where it all began. But there was a big breakthrough that happened in the late 80s, and that was Digital Equipment Corporation came up with the VMS operating system, and then the VMS operating system provided incredibly rich facilities for managing the hardware. So rich that there's really no reason you would want to duplicate that inside the MUMPs virtual machine. The idea was not that, therefore, that we should then upgrade MUMPs to be able to do all the things that VMS could do, but instead, we should do a mapping between the MUMPs virtual machine and the operating system instead of directly to the hardware, right? We would insert a layer in between, and we'd let the operating system manage the hardware, and MUMPs would manage the operating system. And that would be the new set of relationships. And so it's really a very similar diagram to the original notional diagram of the MUMPs virtual machine, except that we've got this thing in the middle. Now, in the beginning, we properly recognized that the operating system is mainly a threat when it comes to portability. Remember, at this point, hardware is changing constantly. Computers are getting faster and faster and faster. And operating systems were changing constantly back then as a result, too. Because although they had existed since time immemorial, the idea of a standard operating system was still really under evolution. And so they were changing rapidly, which meant if we tied our MUMP software to the operating system, we would be just as screwed as if we had tied it to the hardware. We had to insulate MUMPs jobs from that too. So the job of the MUMPs virtual machine became to insulate you from both the hardware and the operating system, not just from the hardware. On top of that, we did recognize the operating system provided some features that could be useful. And so we did want to start exposing those things to MUMPs jobs so that they could use them, but we had to expose them using the native metaphors and idioms of the MUMPs virtual machine. We didn't want to break the portability of the MUMPs virtual machine by saying, now you can tie yourself to all this operating system stuff. So it was a very careful and experimental approach that had to be taken step by step to say, well, I think print queues are really useful, this VMS feature of being able to set up a queue of jobs waiting to print on a printer. So how do we expose a print queue to MUMPs in a way that doesn't lock MUMPs into VMS print queues? And so they would work on that and figure that out. And then they'd say, ooh, I really like this idea of being able to set different job priorities, so that our big expensive jobs can have a low priority and not chew up the computer, and our user jobs can have a high priority so that they get good user response from the system. How do we do that in a generic way that doesn't tie our MUMPs jobs to the operating system? And so throughout the late 80s and early 90s, there was, in fact, I guess to this day, there is a constant incremental process of figuring out how do you expose these operating system features as services that can be available to MUMPs without locking MUMPs into that particular operating system. right? You see the balancing act. Portability is worth. We now know in hindsight it's worth billions and billions of dollars. It's really important to preserve it. MUMP systems tend to be more serious about portability than external systems. Other people will talk about backwards compatibility and they'll talk about portability, but they just have no idea. I mean, medical systems are obsessed with these problems and how to do them. So that's why there was going to be a change over time in the role of the operating system. At first, it was just like a mattress. You lie on it, and otherwise you stay away from it. You put a sheet on it, and you try not to interact with it directly. But over time, we gradually realized it wasn't just a mattress. It was a toy box full of goodies, and we had to figure out how do you expose these things in such a way that you don't get locked into it. So one of the first breakthroughs that we did was invented for the VAXs and then moved to the alphas and other things. And VA is still following something like this model today. And it's called the cluster configuration. And the cluster configuration is built on the idea that we ran with the idea that I showed you here, the replication translation idea, and that we mainly originally used for primaries and secondaries, but sometimes used for applications. But what we did here was we said, you know, what'd be really nice is to be able to separate the really fast background jobs from the interactive users, because the background jobs have a tendency to hog the computer, and then that gets in the way of user performance. So if only we could move all of the print jobs, the background jobs, off onto their own print machine, and we could move all the users onto a user machine, and then we could have a third machine whose whole job is to serve up the data. No users would connect to it. It would just full-time be doing translation and replication to keep the databases in sync on these other nodes, right? And so this got settled upon as a really fast configuration. All the big VA hospitals moved off of the PDPs and onto the VAXs into these cluster configurations, in which we had data servers that served up data, we had compute servers that served up computation resources for users. That's where all the users were, and we had print servers that ran all the background jobs that were intensive and kept the three different ideas out of their way. And we could have multiple compute servers. Right? We already saw before how you could use replication and translation to have multiple. And effectively, that's what's happening here. In a typical configuration, you might have 2, 3, 4, 5 compute servers. You might have 1 or 2 print servers, and then you'd have 1 data server that's really just handling the replication and translation of the database. And so if you've got multiple compute servers, then it raised the issue of load balancing, which is how do you make sure that all your users aren't signed on to one of your compute servers and it's dog slow, and meanwhile these other ones are sitting there not being used at all and users are complaining. And so we had to figure out how to come up with systems to balance the load so that when a user said I want to sign in, that sign in would be routed to whichever compute server was the lightest, right? And we had to do things with the print servers. Taskman has code in him. Our background management system for Vista has code in him that allows him to figure out if he's got multiple print servers, then he might have multiple task managers, and they can each look at their load and say, well, only the one who's on the print server with the lightest load will handle tasks for now. And then when he becomes overloaded and the other guy's light, then they'll switch. And so that way, where the weight is being spread out among these different servers to make sure that they're being used equitably. VA still follows something not unlike this cluster configuration. In a cluster like this, you think of the computers as nodes in the cluster. And sometimes we call them boxes. So when you look in the Vista configuration files for, how do you set parameters based on which computer you're on, sometimes they call them servers, sometimes they call them computers, sometimes they call them nodes, sometimes they call them boxes. There's a field in Vista, a classic field that the Vista hard hats will know called box volume pair, for example. That's what it's talking about. It's saying if you're on volume set ROU, but you're over here on this print server, maybe we should set some parameters differently than we do if you're in volume set ROU, but you're over here on this compute server, right? And again, some of your compute servers might be more powerful than others, things like that. All right, so this is a basic model, and the last big breakthrough that they did was they realized that because the software was integrated and they didn't have to separate it by pharmacy from lab from admissions. They had to put it all together. They eventually realized that reduced the need to share globals and routines between UCIs, because they really only had the one UCI that they were using all the time. They took to calling that UCI VAH for VA hospital instead of PHA for pharmacy or LAB for lab. And ROU, the name of the default volume set was for routines. This is the volume set that has my routines. It really wasn't thought through. But whatever usefulness there was in naming UCIs differently and volume sets differently began to go away, especially when they realized if they didn't have multiple UCIs, not really, then they didn't need a manager UCI to share code and data between different UCIs. They really only had the one. So they began to get rid of the manager UCI and put the manager routines and the manager globals in the same UCI as all the other routines and all the other globals. So we've increasingly moved into a world in which, from the VA's perspective, there's only one volume set and there's only one UCI, and it can run on multiple computers, right? At least that's what it looked like to them in the production sites. The production sites looked more and more like this. So you'd set up a cluster for your live environment. You'd set up a different cluster for your, maybe it wouldn't be a cluster, maybe it'd just be one computer for your test environment, and maybe you'd set up one more for your development environment. And that would typically be how you'd arrange the life cycle in a cluster environment. All right. But while the VA was focused on that, and while Vista development was focused on that. Rising up at the same time, first among the data tree folks and then among the Greystone folks, were MUMPS implementations that took a radical new approach to the relationship between the MUMPS virtual machine and the operating system. And I bring this up because this is more like the world we're in now. Okay? What we're talking about is a world in which if you have 15,000 routines that you're running, and each one is just basically a text file, but for some reason they're stored in a routine directory. Why can't a routine directory be an actual operating system directory? And why can't the routine source files be actual files, text files, that are stored in that directory in your operating system? That's what Data Tree said. I think they were the first to do it, and Greystone did it shortly thereafter. So your routine directory began becoming an actual directory. And likewise, your global directory. If you have binary files that contain your global data, your database in it, why couldn't they be in an actual directory out in the operating system too, right? You don't get the value that you get from routines of being able to inspect them directly because they're not text files, because they've got all these internal pointers and stuff. But at least you can manage, you can use operating system features to manage the storage of those. Where do I put my global data file? Where do I put my routine files? How do I organize the directories? These all become new levels of flexibility that we didn't have before, when it used to be that MUMPS was just a giant blob on the disk, and inside of it, it had all the routine files and it had all the globals, right? Which is how things used to be. So they began pushing things out, and in the last, I think it was 10 years ago, I think InterSystems followed suit, and the cache systems also now store the routine files out in the directories outside. This also came up because when we were starting to expose the interesting services that were available on VMS, it turned out that because DSM did such a good job of insulating the MUMPS jobs from the operating system, there were certain operating system features that you might want access to that you couldn't have because you weren't running as a VMS job. You weren't running in the operating system. You were running inside of the big MUMPS virtual machine box. And that wall between them meant that there's stuff you couldn't do. So in the early 90s, we introduced the ability to start a MUMPS job not inside of the MUMPS virtual machine, but outside in the operating system. And because it was outside in the operating system, it had operating system level privileges, and it could access more things than the rest of the MUMPS jobs could. And so we began managing that. That idea that the MUMPS job might not be inside the box, but might be outside of the box, was again fully brought to life by Data Tree and Greystone. So that, as you see in this, if you just switch back and forth, here there is a MUMPS virtual machine, the blue. But here, there is not a MUMPS virtual machine. Instead, the MUMPS job itself runs the MUMPS virtual machine. Instead of the jobs being inside the virtual machines are inside of the jobs. It's just software that they run. And the operating system has this outer, what used to be a layer under us that we tried to insulate ourselves from, became our native medium, right? So all the shared resources are available out in the operating system. Our jobs are now out in the operating system. And their relationship is to these things that are external. And the place where the MUMPS virtual machine exists as installation is inside. It's in the boundaries of the job itself. This is a big change. I mean, this is huge. So It makes all kinds of things possible. It's just that it's very different from any of the models that we've seen up above, including the other hosted models. It's a completely different way to think about the relationship between your mumps jobs and your operating system, or in our case, between our Vista jobs, that is our VAPALS ELCAP jobs and the operating system. It's very different under GTM than it is under Cache, because GTM puts that mumps job right into the Linux operating system. It's a Linux operating system job. The routines are Linux operating system files. The global dataset files are also Linux operating system files. And as a result, you can use all of the Linux system management capabilities to manage your mumps jobs and your databases. It's hard to explain how big a difference this is. It's like the whole universe turned inside out. You write software very differently. So the thing is, this was so alien to the way that Vista had been developed originally that when we first ported Vista to run on GTM, starting back in 2000, 2001, 2002, all that we could think to do was to hide this. Right? It's just too scary. It's too different. And none of the configuration files were set up to be able to handle this. So what we did is we said, okay, this is how it's actually running. But inside of Vista, where we go into the configuration files and set things up, we're just going to lie through our teeth. We're going to say, even though there's nothing here called a UCI or a volume set, we're going to say, oh, you totally have a UCI. We call it VAH. You totally have a volume set. It's called RAU. GTM doesn't know anything about what we're talking about. It doesn't have UCIs or volume sets, but we're telling Vista that it does. And because we only have one UCI and because we only have one volume set, the way we configure internally in Vista, from Vista's perspective, he never has a problem. He never has to say, what if I'm not in the right UCI? All that code that's specially handled to reach between different environments on DSM or Cache or all the others, it never gets invoked when you're running Vista on GTM, because we just said, you know, there aren't any other UCIs. There's only the one. And there aren't any other volume sets. There's only the one. So this reinforced the thing that happened up above here, where over time, the names of UCIs and the names of volume sets started to become less and less important because we were actually making them match so that we could pull off configuration, cluster configurations. Or in this case, we don't make them match. There just aren't any others. And because there aren't any others, they all tend to be named the same thing, which is where the world is now in terms of OSEHRA and most of the GTM configurations. They're sort of snapshotting an environment. They'll take an environment that Cameron Schlehuber set up on a PLA, Platinum environment inside the VA and released via the FOIA, and then they'll pick it up and distribute it through OSEHRA, and then we'll pick it up from OSEHRA and we'll install it at some Vista site somewhere. And they all have the same UCI and volume set name. You literally can't use them to distinguish them from each other at all because we're just Xeroxing the names from place to place. It has as little meaning as possible. And our problem is this is not a sustainable model for us. This is not a sustainable model because we need to get back to where we can stand up a test site, a test environment, and a development environment, and a live environment side by side on the same computer. We've got to be able to go back and forth, like we're seeing it with Avicenna, where we need to distinguish between what has been installed at Phoenix and what do we have in our development environment. If we can't make that distinction, then we can't do software development. We have to have two different, and it can't just be in a repo somewhere lying there static. Too much of Vista is live and active and dynamic. So we need environments for each of these things that we have to compare to one another. So what's in Phoenix now? What's in our development environment, and then staging we need a staging area for staging what we're going to install in Phoenix next. That's, again, different from either of those. The number of environments we need is multiplying, which means our model that we've been limping along with here since 2000 on the GTM, Vista on GTM systems of pretending there aren't any other UCIs and there aren't any other volume sets, that's not going to fly anymore. We've reached the limits. We've gone past the limits. This doesn't work anymore. We're not doing this anymore. So for the last few minutes, it'll be easy to show you, therefore, what we're pitching. So I think I could do this pretty quick here. In 1995, meanwhile, while all that was going on, in 1995, the new mumps standard came out, and it was radically different from the standards that came before it. It was designed to, for the first time, it was designed to support a standard idea of an environment. Ooh, and I have a typo here. These square brackets that you see here and here, all the way through here, these should be vertical bars. These should be vertical bars. They're the character over the backslash. That's what the standard does. So they had to introduce, for the first time, they were accepting the idea that you could have multiple mumps environments and they might need to talk to each other. An environment as an idea was introduced in the 1995 MUMP standard. So they talked about routine environments where you've got lists of routine names. They talked about global environments where you got lists of global names. They talked about lock name environments where you have lists of lock names. The current standard doesn't talk about device environments, but it uses a lot of arm-wavy language that for the very next standard that's going to follow, they already could see that they were going to have to introduce device environments too. So the next MUMP standard will talk about device environments, and the current one clearly intends to. And you had to be able to talk about where are your MUMPS jobs coming from. And so they introduced the idea of a system. And so I talked about that in one of the earlier presentations. A system's just a pool, from MUMPS's perspective, standard MUMPS's perspective, a system is just a pool of job IDs. And it doesn't have anything more to say about it than that. The way that it did it, it didn't insist that environment was a thing that the MUMPS job was inside, and it didn't even insist that the global environment, routine environment, lock name environment match. It was very flexible, what they introduced. In fact, it's so radically flexible that I don't think anybody's really taken full advantage of this yet. But this is what the MUMPS language now supports. And part of the reason it had to support that was this same standard introduced the ability to use standard MUMPS code to reach from one MUMPS implementation to a different MUMPS implementation. They introduced the idea that instead of just having one kind of MUMPS, you could have cache side by side with DSM, side by side with GTM, each running its own environments. And from inside the cache environment, using the standard extended syntax, you could not only reach into other cache environments, you could reach into a GTM environment or a DSM environment, as long as they all follow the standard that was defined in the 95 standard. So environments, this is why they became important, and this is why the standard finally brought them up as an actual thing. But the way that they did it, there's no UCI and there's no volume set. Notice what's missing from this picture. All of our systems were configured according to UCIs and volume sets in the world, but that's not actually present here in the MUMPS model. So what they gave us instead is they said you could do an environment name. It's a single string that looks like UCI comma volume set. It isn't. It's not two separate values separated by a comma. And the words UCI and volume set don't appear anywhere in the MUMPS standard. But they allowed you to have this kind of flexibility so that you could map it back onto the old structures that you'd created before. This idea that you have a new standard virtual machine that maps onto the older non-standard virtual machines is how they were going to solve the problem of moving ahead and exposing this in the language without breaking anything that existed before. They still talked about the machine. Now they talked about the system. But notice they still don't talk about the operating system. It's missing. Right? Even in the 95 standard, the operating system is still a, la, 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 I can't hear you. So our problem for MASH is that we have to marry this model to the flexibility of the kinds of things that we've done in the past on hosted MUMPS operating systems, which in turn was based upon the earlier ideas of a MUMPS virtual machine that's running the whole computer with UCIs and volume sets. We had to come up with a simple, elegant system that pulls all these things together into one easy metaphor that we can use to name things and lay out our software. And we couldn't restrict ourselves to the standard MUMPS virtual machine, even though we had to be compliant with it, because we have to expose the operating system. It's too important to modern MUMPS systems. So this is what we did. What we did is we said, the global environment, the routine environment, the lock name environment, the device environment, we're going to pretend that that's a UCI. And we'll call the UCI an environment. And we'll say the syntax for environment names is UCI comma vol. Or if you need to abbreviate it, just the UCI part. But, we're going to pretend that this is a UCI. And you could have groups of environments and you could say that together they make up a volume set or a volume. Right? And that can have a name. Now, standard MUMPS won't know anything about that name. And GTM won't know anything about it because GTM doesn't know about volumes or UCIs. But Vista can know about that. And we as sysadmins can know about that. And we can use that to help organize our machines so that so that things make sense and we get all the capabilities that we've had before, but now in a new standard way. Notice that one of the things that we've changed here is that we've wrapped this all with an operating system. So what we've got here is a hybrid between this kind of GTM model in which the operating system is prominent and you have this huge flexibility in routine and global directories, and the standard model in which the operating system isn't here at all. but you've got this mumps virtual machine still. So we've said, okay, the operating system, we're gonna go with this model in which the mumps job contains the mumps virtual machine within it, just like GTM and the others are doing. And that even though the standard allows us to put all these and make all these environments be different things, we're going to make them all be the same thing so that they match together so that we can treat them like we used to do in the old days as a UCI. We're coming up with a simplified, application, if you will, or a single way of configuring based on the earlier idea. And the easiest way to make sense out of this is with our final example on my final slide, how we're laying things out for the VAPALS ELCAP servers. So the way we're doing it is we're doing two environments side by side, a live environment and a test environment. This is what will be running at Phoenix. And we say that they're in a volume together. Okay? And we have a primary and a secondary server. And on the primary server, all the jobs are running the live environment. Nobody's running in the test environment. And on the secondary server, the only jobs that are running on the test environment. Nobody's running in the live environment. The copy, so test on the primary server is replicating off of the secondary. So this is the backup of test in case this one fails. And likewise, the main environment over here on the primary is replicating to a copy of the live environment that's running on the secondary. No users are running against it. It's just accumulating the changes so that if the primary system fails, we can have the users quickly switch over to the secondary and they can get access to all this data while we work on, reconstructing. So this is how we're making sure that you've got the life cycle where you've got test versus live. This is how we're making sure that you've got failover with a primary versus a secondary, and yet we're doing it in a way that's compatible with both the mumps standard and with the way that our mumps implementations and Vista have traditionally thought about the world that's around us. We're imposing the idea of volume sets and UCIs, and the environment is named after UCI comma volume set so that it fits the way that Vista expects to see things, even though there's nothing actually like that in the world. So for next week's call, with this as background, I can show you the layout of the directory, show you the layout of the repos and how we're doing the systems, and that will be, I think, the end of this technical series.
Okay, well, does anybody have any short questions or comments before I release you all to go off and do what you're supposed to be doing?
What do you got, Larry?
Am I on now? Can you hear me?
I don't know, maybe.
Well, my question is, maybe you compare it. It seems like we have, by doing all of this, haven't you lost this enormous advantage of a virtual machine? Or have I we used to have a system you could put on any machine and the developer shouldn't have to worry about it.
So now the virtual machine
is... worry about what system we're on, don't we?
Right. We still have the power of the virtual machine, but now instead of being a big container that all our jobs run inside of, every job itself is running the mumps virtual machine. So the mumps virtual machine is inside the job. That was the shift over that we did with GTM. If I go back and show you the hosted slides, this is how it was on the cluster configurations. But then how GTM did it is they got rid of, they moved the blue that used to be here, got moved inside of the mumps job. And this purple, which used to be under the mumps virtual machine, has now become the surrounding environment. So every mumps job carries with it its own virtual machine inside of itself. Instead of being around everything, it's inside of everything. That's the big shift. And so we're preserving that. Our jobs here, each of these guys is running a mumps virtual machine. And it each assumes the world works a certain way. And the way that we've come up with to make the world look fits the mumps standard so that it's standards compliant, but it's also flexible enough to handle what GTM makes available to us, and also how Vista's been configured historically so that all our configuration files will still work and make sense in this environment. Good question.
Okay. So bring your questions next time or email them to Rick or I or comment on the blog on OSEHRA for the VAPALS program. Have a great day, everybody, and we'll see you next week.
Thanks, everyone.